Hi students, I welcome you all for control system lectures. In the previous class, we started a Nyquist stability criteria. As we know, Nyquist stability criteria is an extension to polar plot in which the plot will be varying from minus infinity to infinity. Right. So we also discussed the relation of open loop transfer function, closed loop transfer function, and characteristic equation. How the poles and zeros are related with respect to open loop transfer function, closed loop transfer function, and characteristic equation. We also discussed the point, critical point, the concept of critical point by considering an example with respect to pole as well as zero. Okay, so in this class we'll go through contour, basic things of contour, and investigation of stability. So what are the conditions that are required to tell the system is stable or not in Nyquist plot. Okay, so if you have g of s, a open loop transfer function, what is the first thing we do is we'll be finding the contour. The contour would be up to our wish, like whatever we wanted to plot, we can consider that as a contour with respect to pole or zero, and which should cover whole right axis, I mean right hand side plane. Okay, if we have a right hand side plane, so this whole thing will be covered while you are considering a contour for g of s, open loop transfer function. Okay, the reason is here in Nyquist stability criteria, we are actually trying to check the stability conditions based on right hand side zeros and poles, right? So if so what we are trying to do is we are trying to map the contour in S plane contour, and we are trying to represent this in g of s plane, right? So this mapping we have discussed in the previous class. Now what I want to let you know is how the contour actually behaves if you have a pole at origin and poles at imaginary axis, and if there are no poles on the in the given transfer function. Okay, so if you don't have first case, in first case 1, if you don't have any no poles no poles in g of s. So in open loop transfer function, if there are no poles, to draw a contour, so contour means it's actually a plot which starts from minus infinity to infinity, which covers whole right hand side plane. Okay, so this will be infinity, this will be 0 plus, and this will be 0 minus, this will be minus infinity. What are this with respect to omega, right? Omega is equal to infinity, omega equal to 0. So this is a whole right hand side plane. We can consider this as a radius which tends to infinity. So whole plane, whole right hand side plane. Okay, so the real axis and j omega axis, this is j omega. So if you are not having any poles, uh, what happens is we'll be dividing this whole contour into 4 parts, right? 4 parts based on the pole location. Here, since there are no poles, we'll be dividing this whole thing into 2 sections. This is one section C1, and this is another section C2. Okay, this is also C2. Irrespective of the plane, whether it is a negative plane or positive plane, we'll be considering this whole right hand side as C2 and whole imaginary plane as C1. Okay, so these are the 2 points. In order to investigate the presence of poles on g of s, this is g of s plane, on the g of s h of s right hand side plane, So this is actually C, like it can be C1 and C2. Overall it is C. C means actually enclosure. Okay, C is considered in entire right hand plane. Okay, so the direction will be clockwise direction. This is about the contour. So the infinite line segment, this is actually line segment in imaginary axis, and C2 is with infinite radius. C2 will be with infinite radius. So if you are considering C1 S equal to j omega, if S equal to j omega, S will be varying, S will be varying from minus j omega to j omega, where omega is minus infinity to infinity, or directly we can tell it as j infinity to minus j infinity to plus j infinity. Okay, minus j infinity to plus j infinity, SC1. Okay, C2, to get any point here somewhere in the right hand side, any point if you consider, so to get the details of that particular point, C2 can be given as S is equal to limit r tends to infinity, that is radius tending to infinity, r into e power j theta, right? So since it is actually going from 90 degrees, it is actually 90 degrees, right? This is 90 and this is minus 90. It actually starts here and goes this way and ends at minus 90. Therefore, theta will vary from 90 to minus 90. 90 degrees to minus 90 degrees. So this is in the first case. Similarly, in the second case, if you consider a pole at origin, okay, let us consider a pole at origin. So let us draw rho plus j omega, and if any pole is there at origin and that is undefined for the given contour actually. So the contour won't touch in that particular pole. It will start after the pole, then it will tend to infinity, and the similar path it will be followed as previous path, and again it will come till infinity. So in this case, again after here we need to join this, right? We need to join this point. So this will be infinity, this will be minus infinity, and here this is actually j0 plus and this is j0 minus. Okay, so this is actually r tending to infinity, this is j omega. So from here what we can take is this is infinite line, infinite frequency. This part we can take it as C2. This can be taken as C1, and this whole thing anyway we can take it as C2 itself. So this is also C2, and this particular part, this we can take it as C3, and here one more is there, this particular part, this we can take it as C4, right? Uh, so for this particular plot contour, this is called Nyquist contour. Nyquist contour. So for this particular contour, if you are estimating C1, C2, C3 and C4, how they actually varies. So here, this particular C1 is varying from J0 plus to J infinity, and the C2 will be varying from j infinity plus, so you can take it as j infinity plus, and j infinity plus to j infinity minus. Okay, so this here actually we can take infinity frequency, and this is given as yes, here s is equal to limit r tends to infinity, r into e power j theta, where theta will be from varying from same as the above case. Theta will be varying from 90 degrees to minus 90 degrees. Okay, so in the other case here, this particular case, where if you are considering at radius r tends to 0, r tends to 0, this can be written as r of e j theta limit r tends to 0. So for this is for case C4. Okay, this is for C4. And C3 we discussed, C3 will be varying from minus C3 will be varying from J infinity minus to J0 minus, with the angle of 0 minus 90 to 0 minus would be 90 itself, to 90. And another case we can take, that is if you have imaginary poles, we have some imaginary poles, how can we draw that? Say if you have poles here, here and here, in this case how can we do is just skip the things. Here you can skip the pole and draw till here, skip it, draw here, and go till minus infinity, draw here and skip it here. So this is how it moves actually. Okay, so in this case this can be, so starting from the case 1, this can be considered as C1, say 2, this is C3, C4, okay, this is C5, similarly this is C6, C7, C8. Okay, so this is how the contour of g of s in the s-plane looks. So by making use of this contour, we'll be mapping this contour and writing encirclement in g of s-plane. So this is nothing but Nyquist plot. And this is Nyquist contour. So let us see the stability conditions now. So Nyquist plot is actually applicable for minimum and non-minimum phase. That means if you have a right hand side 0, then the system is said to be having a non-minimal phase. Okay, whereas polar plot is applicable only for estimating the stability of minimum phase systems. In Nyquist plot, we can estimate the stability of non-minimum phase system as well. Okay, so there are few conditions to be noted based on n value, right? As we discussed in the previous class, n is equal to p minus z. So with respect to origin in the sense, if you are considering characteristic equation 1 plus g of s, we will be estimating encirclement with respect to origin. If you have actually 1 plus g of s plane, 1 plus gs plane, and if it is gs plane, we will be estimating with the critical point, that is minus 1 plus j0. Okay, If it is 1 plus s, we'll be estimating with respect to origin, and if it is g of s, we'll be estimating with respect to minus 1, this point. Okay, so n is number of encirclements for 1 plus g of s characteristic equation. If you are considering CE, then n is number of encirclements of 0 comma 0, that is at origin, right? And if n greater than 0, if n greater than 0 means p will be greater than 0. P is greater than 0. Number of poles will be greater than number of zeros. In that case only we'll get n is greater than 0, and if this case is satisfied, we'll get anti-clockwise direction in 1 plus g of s plane, that is Nyquist plot. Whatever the contour we are plotting in 1 plus g of s plane is with respect to origin, and that will be anti-clockwise direction if n greater than 0, right? If n less than 0, it will be clockwise direction. Okay, so number of poles now, p will be number of open loop transfer function poles in right hand side plane in RHP, whereas zeros, z is number of open loop transfer function zeros in RHP. So this is one case. In second case, we'll be estimating with respect to g of s. If you are considering a Nyquist plot with a critical point, this is important, critical point, that is minus 1 plus j0, minus 1 plus j0. If you are considering, the point will be here. This is just a shift of 1 here. From the characteristic equation, we are considering only this part. That means we are shifting this characteristic equation with 1 on left hand side. Okay, in this case, number of encirclements, n will be number of encirclements with respect to minus 1 comma 0, and p will be number of open loop transfer function poles in RH plane, right hand side plane. Okay, and z will be number of closed loop transfer function zeros. Okay, closed loop transfer function zeros in RH plane. So for the closed loop stability, z is equal to 0. If there are no zeros, okay, there are no zeros, let us consider the cases here. For closed loop stability, z is equal to 0. That means there are no zeros. No zeros in the closed loop expression. That is T of S. So in case 1, if n is greater than 0, we'll get anti-clockwise direction, and encirclement will be with respect to minus 1 comma 0. Okay, and if z equal to 0, okay, this condition, if z equal to 0, for closed loop stability, number of open loop poles in RH plane should be equal to number of encirclements. Okay, for closed loop stability, number of open loop poles in RH plane will be equated to number of encirclements. Number of encirclements. Okay, this is case 1. And in case 2, if n is equal to 0, n equal to 0, here n is greater than 0. Now in case 2, if n is equal to 0, in this case no encirclement in -1 comma 0 axis. Okay, at this point -1 comma 0 point there is no encirclement, because here n equal to 0 means number of poles and number of zeros will be equal, right? Number of poles is equal to zeros. So in this case closed loop system is stable if poles, closed loop system is stable if p is equal to 0. If p is equal to 0 or no closed loop open loop or no open loop poles in right hand plane or open loop system is stable. So in this case open loop system is said to be stable. Both closed loop system and open loop system will be stable in this case. Okay, and there is no encirclement around -1 comma 0 point. And in case 3, n is less than 0. Here if n is less than 0, that means zeros will be greater than poles. Okay, number of zeros will be greater than poles. That means clockwise direction, right? So Nyquist plot will be in clockwise direction, clockwise encirclement of -1 comma 0 point. Okay, so this in this case system is closed loop system is guaranteed unstable. So these are the points to be remembered. So in next class we'll solve a numerical problem where we'll make use of all these steps, and we'll start estimating the system stability, and we'll determine for the range of k values, for the range of k where and all the system, that is the kind of relative stability. We can, in this method we can actually estimate relative stability as well as absolute stability. Okay, so remember all these points. We'll make use of all these points and solve the numerical problem in the next class.